So if you're given this, and you're just simply asked to balance the equation, and the only thing you're told is there's water. Okay, this is taking place in some kind of water environment. We first have to know what kind of equation it is. Okay, its classification of the equations is only a step to figuring out what kind of products you're going to need. Okay, or what kind of driving force you need. If you have a single replacement reaction, then all you have to do is look at the reactants and the activity series to figure out if you have a driving force. If it's a double replacement, you've got to figure out what your products are going to be and figure out the physical states of those products to see if you have a driving force. Okay? So we need to know if this is a double replacement reaction or a single replacement reaction or something else. Okay? So what classification of formula do we have here? What kind of compound do we have here? Okay? She says it's aqueous, but I want to know what another kind of classification. What? Well, I'm not classifying the whole equation. I'm classifying just the compound. It has a polyatomic ion, so that makes it an ionic compound. Okay? It's ionic. It's in two parts. This is a polyatomic ion, and this is the other part of the compound. So this is our sort of A-B parts. Okay? Ionic compounds and acidic compounds are always two parts. Okay? And generally speaking, not always, but generally speaking, you can expect the polyatomic ions to stay together. They don't break up. So we treat this like it's a single thing and not two different things there. How about this one? What kind of compound is this? Covalent, ionic, what is it? It's ionic because it's made of?
Two more.
Well, not two or more. It's a metal and a non-metal. So those are the two ways you can look at a formula and figure out if it's ionic. If it is either metal combined with non-metal, or it contains a polyatomic ion. In either case, those are going to be ionic compounds. How do you know when you have an acid?
They have
Has a hydrogen on the front. Okay, so both ionic compounds and acids are two-part compounds of the type that will go through these kind of reactions we're talking about here. So if we're going to use this A-B format, then we can call this C and D. All right. And what's going to happen then is if this reaction takes place at all, the front part of this has got to go with the back part of that. And when you write the new formula, the front part stays the front. So A is going to go with D, and it's going to be AD over here. Okay? So we're going to put AG with Cl. Now I haven't balanced the formula or anything. I've just put those two together for the moment. Okay? And then what I'm going to do then is take this front part of this and put it with the back part of that. And we're going to treat this polyatomic ion like it's one thing, not two, because it's going to tend to stay together. We're just going to put them together. We're not going to balance the formulas yet. Just stick them together. Magnesium and nitrate. Okay? Now I need to balance the formulas, but if there's no reaction, there's no real reason to. Because if there's no reaction, I'm just going to mark it out and put NR. So the thing I need to do to find out if there's going to be a reaction is determine the physical states of all these compounds. And we're going to use the the solubility rules to do that. Okay? So in your test references, the solubility rules are found on this page. If you don't have your test references out right now, unless you've got them memorized, you should have them out right now to follow along so you can practice this stuff. Okay? You with me, Robbie? Okay? Alright, so what we want to do is to find either silver or nitrate listed in the solubility rules. Alright, for the first one. Well, it says right up here at the top, the very first thing, that all nitrates are going to be in this soluble section. All nitrates are soluble. And I'll read through the whole thing there, and there's no exceptions. So anything that's bonded with nitrate is going to be soluble. Soluble is what it can do. You have to determine if it's going to be aqueous, and you determine it's going to be aqueous if it's both soluble and there's water around. Well, in this case, there is water around, So we will identify this as being aqueous. But since we figured out that all nitrates are aqueous, I could go over the other side and go ahead and label this one aqueous, because all nitrates are aqueous and there's no exceptions. Alright, so let's look at this. I want to find either magnesium or chloride. I look on the solubility rules, and chlorides are listed on this second item here. It says all chlorides, bromides and iodides, are going to be soluble unless they're bonded with silver. Well, that's not bonded with silver. They're bonded with lead. Well, that's not lead. Or they're bonded with mercury 1, and that's not mercury 1. So this must be aqueous. Okay, if it's soluble and water is around, then you're going to determine that it's aqueous. Okay, but it did say that chlorides that are bonded with silver are an exception. So while most chlorides are soluble, and therefore if there's water around it will be aqueous, chlorides bonded with silver are not. So what physical state do I assign to this? A solid. Okay? Now we're ready to go and balance the formulas. But the reason we're ready is because we've identified a driving force. Since we have a solid here, that's one of our three driving forces for double replacement reactions. The three driving forces are the formation of a solid, the formation of water, or the formation of a gas. And we have one of those three, so we've got a driving force.
What would be the formation of water for the driving force? AC?
It's just water is just HOH or H2O, and we just list that as L. In a double replacement reaction, water will be a liquid.
Okay.
Water is a gas in a combustion reaction, but not in almost any other kind of reaction, unless I tell you something, okay, that will tell you otherwise. I mean, there are reactions I tell you, well, this is happening in a real hot environment. You know then that water's got to be gas. Okay. All right. So let's balance the formulas now. Okay. These two formulas were already balanced. We're going to leave them alone. I want to go over here and look for the balance for silver and chloride. What charge do we assign to silver? Really? 2 negative? Where do you find that? The charge on silver.
On the O.
The periodic table with oxidation numbers, that's also in your test references here. We're going to look down here and find silver, and it says there's only one charge on the silver, and that's always a 1 plus. So this has to be a 1 plus on the silver. Okay. And then what's the charge on the chlorine? 1 minus. Now chlorine has a bunch of different possible choices of oxidation numbers. But we need this whole thing to equal 0, and the only way for that to happen is silver's got to be 1 plus, then the chloride has to be some kind of a negative, and the only negative assigned to silver is that 1 negative here at the bottom. So it's got to be that 1 negative. So how many of each of these do I need now to make this formula, this equation here, work out to be 0? You need one of each of these, don't you? Okay? Which means I only need one of those and one of those, so that I don't have to do anything with that one. That one's already balanced. You don't have to put any subscripts in there. Let's go over here to magnesium and nitrate then. What charge do we assign to magnesium? Magnesium is always 2 plus. Okay? What charge do we assign to nitrate? 1 negative. So let's use that same sort of setup here. Alright? Well, we need to know what kind of coefficients will go in front of this to make this whole problem work out to be 0. 1 magnesium and 2 nitrates. Does that make sense to everyone? Okay. Which means I need 2 nitrates. Well, I can't just put a 2 here. That would look like I had 32 oxygens. I need a parentheses around this, and the 2 outside means I have 2 nitrates, which is what I need. Okay? All right. And that's kind of crowded up. I wish I'd moved my AQ over a little bit, but we'll work with it. So now that we've got our formulas balanced, and we've assigned physical states, and we know there's a reaction that's going to take place, we're ready to balance the the equation, and yes, we do that with an atom inventory. Okay? So, we're going to list all of our elements here, Ag, and N, and O, and Mg, and Cl. We're going to make our little spreadsheet or grid chart. Yes.
Do we need to show the, what you just did with the 1 negative and 2?
No, the only thing I'm going to look at is this. But if you can't figure it out in your head, it's better to put it down and show me how you got that, so that if you make a mistake, you won't lose. You might not lose as many points. It depends on how I've set up my rubric to grade. And if I'm giving points for showing me how you did your work, then you would get credit. You might get partial credit for it, so you don't lose as many points. It's always better to show all your work than to leave anything out. And there are a lot of things where I require you to show all your work. Okay? All right. So we're going to count all of our elements now. So in this formula, there's no subscript afterwards. And right now, there's no coefficients out in front, so that's just one silver. No subscripts after the nitrogen, so that's one nitrogen. The subscript after the oxygen means I have here, this 3 means I have 3 oxygens here. I have 1 magnesium. The 2 here means I have 2 chlorines. On the other side, I've got 1 silver here. I've got this 2 outside the parentheses means I've got 2 nitrates. Now in the nitrate polyatomic ion, there's only 1 nitrogen. But since I have 2 polyatomic ions, there are overall 2 nitrogen atoms on this side of the equation. So I need a list of 2 here. And then I also, for the same reason, will have 6 oxygens. And I've got 1 magnesium and 1 chlorine. You always save oxygen for last. The other 2 things that are unbalanced right now are nitrogen and chlorine. Let's just start at the top with nitrogen. Since I have 2 on the right and only 1 on the left, let's put a 2 in front of the species that contains the nitrogen. Okay, and that gives us 2 silvers, 2 nitrogens, and since I had 3 oxygens in the formula and 2 times everything there, that means I've got 6 oxygens now. Okay. Alright, so now we've got our silvers unbalanced. Let's go to this side. And I've got 2 silvers on the left and 1 on the right. We need a coefficient 2 in front of that formula there. And that'll change the number of silvers to 2. And it changes the number of chlorines to 2. And everything's balanced out.